Welcome back to The Deep Dive, the show where we slice through complex topics, extract the most important insights, and make you well-informed quickly. Today, we're plunging into the very bedrock of digital security. CISSP Chapter 11, focusing on secure network architecture and components.
That's right. And if you think about it, almost everything we do digitally, sending an email, streaming a movie, it all relies on networks.
Totally.
And protecting that data means understanding how these networks are built, how they communicate, and, well, crucially, how to secure them from the ground up.
Right.
This isn't just about technical definitions. It's about seeing those hidden layers that protect or, expose your information every single day.
Yeah.
Get ready for some real aha moments as we connect the theoretical to the intensely practical.
Okay, let's unpack this. When we talk about networks, data communication security, we often start with, well, models. Specifically, the Open Systems Interconnection, OSI, model. It feels a bit abstract, maybe. But why do we even need a conceptual blueprint like the OSI model for something as complex as network communication? For me, it's like a complex construction project where you have different teams, each with their specific roles and responsibilities. Is that fair?
That's a perfect analogy, actually. You absolutely need rules for how different parts of a system interact. In networking, these rules are called protocols.
Protocols, right?
Yeah, a protocol is simply a set of rules and restrictions that define how data is transmitted over, well, any network medium. The real genius of the OSI model, even though it's more of a conceptual framework in transmission control protocol, internet protocol, TCP/IP, is what we actually use.
Right, the practical one.
Exactly. But the genius isn't just about interoperability. It's that it gives us this precise mental map for security. When something goes wrong or, when you're designing defenses, you can pinpoint exactly which layer is vulnerable or where a control needs to sit. It's like our security GPS. And the OSI reference model itself was developed by the International Organization for Standardization, ISO, way back in the late 1970s to establish a common communication structure.
So it's a theoretical construct, a way to break down a super complex process into, manageable chunks. The OSI model divides networking tasks into 7 distinct layers.
Yep, 7.
And we're going to dive into each of them, starting from the top, where we, the users, typically interact, down to the very physical connections.
Precisely. Let's begin with layer 7.
Layer 7, the application layer. This is where we, the users, directly interact with the network almost without even realizing it. Your web browser, your email client, or that video conferencing software you use every day. So it's about how the software services actually communicate.
You're absolutely right. The application layer is responsible for interfacing user applications, network services, and the operating system with the protocol stack. It's basically how software services communicate and initiate requests across the network.
Yeah.
It's crucial to understand, though, that the applications themselves aren't within this layer. Rather, this layer provides the protocols and services needed for those applications to transmit files, exchange messages, connect remotely, that kind of thing.
Got it.
For security, this is often the first point of user interaction, and so naturally it's a common target for attacks like phishing or malware delivered through web browsers.
Makes sense. Moving down the stack, we arrive at layer 6, the presentation layer. If the application layer is where we see the software in action, then the presentation layer feels like the translator or formatter of the network. Is that right? What exactly is it doing with our data?
It's doing exactly that. It's transforming data into a format that any system following the OSI model can understand. This layer handles common data structures, formatting rules, and it's also responsible for critical security functions like encryption and compression.
Encryption, okay.
Yeah, and what's particularly interesting from a security perspective is that encryption can actually occur at various points within the network stack. For example, you can have encryption that happens even before the data hits the application layer, or more commonly, at the transport layer, using transport layer security, TLS.
Ah, TLS, right.
And in virtual private network, VPN, encryption can also operate at different layers, depending on the specific technology. This layered encryption strategy is really a key part of defense in depth.
Right, multiple layers of protection.
Exactly. Makes it harder for an attacker to just tap into one part of the network and read everything.
That's fascinating, so many places for encryption. If the presentation layer is about making data understandable and secure across different systems, what does layer 5, the session layer, do? Is it about, keeping the conversation going?
You've hit on a key aspect there. The session layer is responsible for establishing, maintaining, and terminating communication sessions between two computers. Think of it as the conductor of a conversation. It manages the dialogue discipline, meaning it determines if communication is one way, like a traditional radio broadcast, simplex.
Like old radio.
Right. Or two-way, but only one direction at a time, similar to a walkie-talkie, have duplex.
Over.
Yeah. Or two-way simultaneously, like a phone call, full duplex. It also establishes checkpoints for grouping and recovery, and it can retransmit protocol data units, PDU, that failed or were lost, ensuring that a conversation can pick up where it left off.
So it's managing the flow.
Precisely.
Yeah.
And from a security standpoint, if someone disrupts that session, they can break or even hijack your entire communication.
Right, that makes sense. Now we're at layer 4, the transport layer. This one feels like the post office sorting mail, ensuring it gets where it needs to go reliably, and perhaps making sure all the pieces of a letter arrive in the right order. What's its main job?
You're absolutely right about the post office analogy. The transport layer's primary responsibility is to manage the integrity of a connection and control the session. It establishes communications between nodes, defines session rules, and crucially, verifies message integrity to determine whether data has been lost.
Okay, integrity is key.
Very key. It provides end-to-end transport services, handling segmenting data, sequencing them correctly, performing error checking, and controlling the flow of data. The key protocols you'll encounter here are Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, along with Transport Layer Security, TLS.
So TCP and UDP are fundamental here. I know TCP is often described as reliable and UDP as unreliable or maybe connectionless. Can you explain the TCP three-way handshake that ensures that reliability?
Of course.
Yeah.
TCP is connection-oriented and employs reliable sessions, meaning it guarantees delivery. The three-way handshake is how it establishes that connection.
Okay.
First, the client sends a SYN, synchronized flagged packet, to the server. Right. The server then responds with a SYNACK, synchronized acknowledge, flagged packet back to the client.
SYNACK.
Yep. Finally, the client responds with an ACK acknowledge flagged packet to the server. Once that's complete, a reliable connection is established and data transfer can begin.
So SYN, SYMAC, ACK. Got it.
Exactly. For disconnection, TCP typically uses a FIN finish, flagged packet for a graceful shutdown, or an RST reset flagged packet for an abrupt termination. That three-step handshake is literally the digital equivalent of, hello, are you there? Yes, I'm here. Are you there? Yes, I'm here too. Let's talk.
Huh. Okay.
And that ensures reliability. UDP, on the other hand, is connectionless and offers no standard error detection or slow control. It's often used for real-time streaming where some data loss is acceptable for speed, like video or audio. Speed over reliability.
Right. Like live video calls?
Perfect example.
Okay.
A few drop pixels are better than a long delay.
That makes a lot of sense. So if the transport layer is managing that reliable connection, layer 3, the network layer, must be the GPS navigator, right? Getting the mail to the right city or, indeed, the right continent.
Precisely. The network layer is responsible for logical addressing, meaning Internet Protocol, IP addresses, and routing. It includes the source and destination IP addresses in its header, guiding data across different networks.
So IP address is live here.
Yes. It also manages error detection and controls node data traffic. While IP is dominant today, there were non-IP protocols historically, like Internetwork Packet Exchange, Sequence Packet Exchange, IPXSPX, and AppleTalk.
I remember those.
Yeah, legacy stuff. These are problematic for modern firewalls and should generally be blocked because they can sometimes be encapsulated in IP and bypass security controls.
Finicky.
The primary hardware device functioning at layer 3 is the router. Routers determine the best logical path for packets based on factors like speed, hop count, and preference using routing tables.
Okay, routers make the decisions.
They do. And there are different types of routing protocols. Distance vector protocols like Routing Information Protocol, RIP, and Interior Gateway Routing Protocol, IGRP, which build tables based on distance metrics. Then link state protocols such as Open Shortest Path First, OSPF, and Intermediate System to Intermediate System, ISIS, provide a more global view, considering speed, latency, error rates.
More sophisticated.
Yes. And finally, path vector protocols like Border Gateway Protocol, BGP, which maintain routing tables for autonomous systems across the internet. That's the big one for the internet itself.
BGP. Right.
From a security standpoint, it's crucial to configure routers to accept updates only from authenticated routers, restrict administrative access, and regularly update router firmware. Basic hygiene, but vital.
Okay, now we're really getting down to the nitty-gritty. Layer 2, the data link layer. This is where the local delivery happens, making sure the right package gets to the right house on the street, perhaps.
That's a perfect way to put it. The data link layer is responsible for formatting the packet for transmission, and it defines the hardware, topology, and specific technology being used, such as Ethernet, which adheres to the IEEE 802.3 standard.
Ethernet, got it.
This layer adds source and destination hardware addresses, commonly known as Media Access Control (MAC) addresses. These are 48-bit binary addresses, often represented in hexadecimal.
The MAC address, like the physical serial number for the network card?
Kind of, yeah. The first 3 bytes of a MAC address are the Organizationally Unique Identifier, OUI, which denotes the vendor that manufactured the network interface.
Ah, OUI. Interesting.
A key protocol at this layer is the Address Resolution Protocol, ARP, which resolves IP addresses to MAC addresses.
ARP translates IP to MAC.
Exactly. Devices like switches and bridges also operate at layer 2. They support MAC-based traffic routing, meaning they send frames, which is what a packet is called, at this layer 2 specific MAC addresses, efficiently directing traffic within a local segment.
Okay, switches are smarter than hubs then.
Much smarter. And from a security perspective, this layer can be surprisingly vulnerable, as we'll discuss later with ARP poisoning.
Right, looking forward to that. And finally, layer 1, the physical layer. This is the very foundation, the literal wires, fiber optic cables, or, the airwaves themselves.
Exactly. The physical layer is responsible for converting a frame into bits for transmission over the physical connection medium. It's where you find network hardware devices like network interface cards, NICs, hubs, repeaters, concentrators, and amplifiers.
The actual hardware bits.
Yep. These devices perform hardware-based signal operations, like sending a signal from one connection port out on all other ports, that's a hub, or amplifying a signal to support longer transmission distances. This layer, while seeming simple, is where physical security and even basic signal integrity can impact overall network resilience.
So as data travels down the stack, from the application layer to the physical layer, it gets progressively packaged. Is that what encapsulation is, like putting a letter in an envelope, then that envelope in a box?
Yes, that's precisely encapsulation. It's the process where, at each layer, the message receives an additional header, and in some cases, a footer. Your analogy is perfect, adding layers of packaging as it moves down an assembly line.
Okay.
When the data arrives at the receiving computer, the inverse process, called de-encapsulation, or sometimes decapsulation, by the Internet Engineering Task Force, IETF, occurs. As the message moves up the stack, each layer strips off its corresponding header and footer until the original data payload is revealed at the application layer.
Unpacking the gift.
Exactly. This concept also highlights peer layer communication, where each layer on the sending device logically communicates with its counterpart layer on the receiving device. Layer 4 talks to layer 4, layer 3 to layer 3, and so on.
Gotcha.
This layered approach is why a breach at one layer doesn't necessarily compromise everything, but it also means an attacker might target a specific layer.
That makes perfect sense. And I've heard some fun ways to remember these layers, like, please do not teach surly people acronyms if you're going from physical up to application.
Yes, that's a classic.
Or all presidents since Truman never did pot, for application down to physical. Whatever works for you to remember them, right? It's about getting that conceptual blueprint down. Okay, so we have this grand conceptual OSI model, which really helps us understand the theory. But then there's the Transmission Control Protocol, Internet Protocol, TCP/IP model. How does it compare to the OSI model in the real world? Is it, simpler?
It is simpler, yes. The TCP/IP model, also known as the Defense Advanced Research Projects Agency, DARPA model, or simply the Department of Defense, DoD, model, is a more widely used in practical reality. It's a 4-layer model, typically simplified into application, transport, internet, and link.
4 layers instead of 7.
Right. Essentially, TCP/IP's layers combine functionalities seen in the OSI model. For instance, TCP/IP's application layer combines the functions of OSI's layers 5, 6, and 7, the session, presentation, and application layers.
Bundles them together.
Exactly. And TCP/IP's link layer handles what OSI's data link and physical layers do. It's important to remember that the TCP/IP suite was developed before the OSI reference model was formally published, which explains why their structures differ.
Okay, that makes sense.
What's truly insightful, and maybe a bit alarming, is how many fundamental TCP/IP vulnerabilities stem from design choices made decades ago.
Yeah.
Prioritizing simplicity and speed over robust security back then.
We're still living with those decisions.
We really are. It's a constant battle of retrofitting modern defenses onto an ancient yet indispensable foundation.
So it's more consolidated, more practical for what's actually running our internet today. But what are some of the inherent vulnerabilities in the TCP/IP model that security professionals really need to worry about?
Oh, plenty. Despite its widespread use, TCP/IP stacks have numerous vulnerabilities that attackers constantly exploit. We often see issues like buffer overflows, where a program writes data to a buffer beyond its allocated size.
Right, overwriting things it shouldn't.
Exactly, potentially allowing an attacker to execute malicious code. SYN flood attacks are common, where an attacker sends a flood of SYN requests to a server but doesn't complete the three-way handshake, exhausting server resources and causing a denial of service, or DOS.
Overwhelming the server.
Precisely. There are various other DOS attacks, fragging attacks that exploit how IP fragments are reassembled, and oversized packet attacks. Spoofing attacks, where an attacker disguises themselves as a legitimate entity by forging network addresses, are also prevalent.
Pretending to be someone else.
Yep. We also contend with adversary in the middle, or AITM, attacks, where an attacker secretly relays and maybe alters the communication between two parties who believe they are directly communicating.
The classic eavesdropper who messes with the message.
Exactly. Hijack attacks, where an attacker takes over an existing legitimate session, and various coding error attacks due to flaws in implementation are also concerns.
And what about attacks that are less active, more sneaky?
Good point.
Yeah.
Beyond active attacks, TCP/IP is also subject to passive attacks like monitoring and sniffing. This involves an attacker observing network traffic without directly interacting with it, allowing them to gather information like unencrypted data or session details. Eavesdropping falls into this category, where communications are secretly listened to.
Just listening in.
Right. And these passive methods are often crucial for information gathering before launching a more active attack later on.
Now let's talk about the addresses that guide all this data across the internet. Internet protocol, IP addresses, like the street address for data on the internet. What's the difference between Internet Protocol version 4, IPv4, and Internet Protocol version 6, IPv6? Seems like a big jump from 4 to 6.
It is a big jump. So IP is the protocol at the network layer responsible for data packet addressing and routing. IPv4, which you're likely most familiar with, uses 32-bit addresses and is still the most widely used.
The ones that look like 4 numbers separated by dots.
That's the one. You might have heard about Class A, B, and CIP addresses. These were historical ways of allocating address blocks based on the first few bits. Well, that specific system isn't really used for new allocations today. Understanding that original idea of fixed-size blocks helps appreciate why we moved to more flexible methods, like classless interdomain routing, CIDR.
GIDR, right? More flexible.
Much more flexible and critical for efficient network design and security today. For testing, IPv4 also has the loopback address 127.0.0.1, which the system uses to refer to itself. Ping 127.MIDRA 0.1 is a common first step in troubleshooting.
Okay. And IPv6.
Internet Protocol version 6, IPv6, uses 128-bit addressing.
Wow, 128 bits. That's a lot more addresses.
A vastly larger number. We essentially ran out of IPv4 addresses. IPv6 is being rapidly adopted for both public and private networks. It also introduces new features like scoped addresses for specific network regions, auto-configuration capabilities making setup easier, and quality of service, QoS, priority values that allow administrators to group and prioritize network traffic.
So you can prioritize, say, voice calls over file downloads.
Exactly. IPv6 also offers Dynamic Host Configuration Protocol version 6, DHCPv6, which can be stateful, assigning specific IPv6 addresses, or stateless, which uses stateless address auto configuration, SLAAC, allowing devices to generate their own addresses based on router advertisements.
So IPv6 seems superior in many ways. What about the transition from IPv4 to IPv6? Is it smooth? And are there security implications during this, coexistence period?
The transition and migration are ongoing, and yeah, they present several security concerns. With a 128-bit address space, IPv6 offers vastly more source addresses for attackers to use, potentially making traditional IP filtering and block lists less effective.
Harder to block attackers if they have trillions of addresses.
Pretty much. Furthermore, if not securely deployed, IPv6 could serve as a covert channel, bypassing existing IPv4-centric security controls and potentially operating unfiltered.
Sneaking traffic past the old guards.
Right. To manage the coexistence of IPv4 and IPv6, we use mechanisms like dual stack, where both protocols operate concurrently on the same device or network.
Running both at once.
Yes. And tunneling, which encapsulates one protocol within another, such as IPv6 packets within IPv4, to traverse parts of the network that only understand IPv4.
Got it.
Oh, and both IPv4 and IPv6 packets have a time-to-live, TTL, or hop limit field. This is a counter that gets decreased by each router the packet passes through. When this limit reaches 0, the packet is discarded, and an Internet Control Message Protocol, ICMP, Type 11 Timeout Exceeded Error Message, is sent back to the origin.
Ah, so that's how traceroute works.
Essentially, yes. It prevents packets from looping endlessly around the network.
Beyond just addresses, there are crucial protocols that keep the network talking and that often pop up in security discussions. What are Internet Control Message Protocol, ICMP, and Internet Group Management Protocol, IGMP, and how are they relevant to security?
Okay, so ICMP is fundamentally used to determine network connectivity and status. It's the protocol behind utilities like ping and traceroute.
Ping. Everyone knows ping.
Exactly. It allows you to see if a remote system is responding and how data traverses the network. However, ICMP features can be exploited in denial of service, or DOS, attacks. Examples include the old ping of death, where specially crafted, oversized ICMP packets could cause systems to crash.
Nasty.
Smurf attacks, which flood a network with ICMP echo requests, spoofing the victim's address, causing all the replies to flood the victim. And simple ping floods, just overwhelming a target with ICMP traffic.
So it's useful but dangerous.
Can be, yes. For IGMP, or Internet Group Management Protocol, its job is to manage multicasting, which is the transmission of data to multiple specific recipients simultaneously, like streaming video to multiple subscribers at once. Less commonly exploited, but still part of the picture.
You mentioned Address Resolution Protocol, ARP, earlier as a Layer 2 function that resolves IP addresses to MAC addresses. It seems simple, but you hinted it has some big security issues, right? Like someone pretending to be another device.
That's absolutely correct. ARP's simplicity is also its biggest vulnerability. The primary concern is ARP cache poisoning, also known as ARP spoofing.
Poisoning the cache sounds bad.
It is. An attacker sends falsified ARP replies to a network device, which then updates its dynamic ARP cache with incorrect IP to MAC mappings. This can involve sending gratuitous ARP or unsolicited ARP messages that announce an incorrect MAC to IP mapping without being requested.
So they lie about who has which IP address.
Exactly. This allows an attacker to intercept, modify, or even block traffic intended for a legitimate device by making network devices send traffic to the attacker's MAC address instead. It essentially puts the attacker in the middle of a communication.
The classic man in the middle, but at Layer 2.
Precisely. I remember once debugging a really weird network issue for hours, trying everything, only to find out it was an ARP poisoning attack rerouting traffic. Like someone rerouting all the mail in a city to one wrong address. The chaos was immediate.
Wow. So what are the defenses against ARP poisoning? How do you stop someone from lying about their address?
Well, one defense is to use static ARP entries. These are manually configured IP to MAC mappings that cannot be overwritten by ARP replies.
Manual configuration sounds tedious for large networks.
It is. It doesn't scale well in large dynamic networks. More practical defenses include switch port security, which can limit the number of MAC addresses learned on a port, or bind specific MAC addresses to ports, preventing unauthenticated devices from communicating and potentially blocking malicious ARP replies.
Okay, locking down the switchboards.
Right. Also, host-based intrusion detection systems, HIDS, and host-based intrusion prevention systems, HIPS, running on the actual computers can detect and block unrequested or suspicious ARP replies. And tools like ARPWatch can monitor for changes in ARP mappings and alert administrators.
So multiple layers of defense again.
Always the best approach.
Okay, let's shift gears to the domain name system, DNS. This is like the phone book of the internet, right? Turning human-readable names like www.google.com into IP addresses that computers understand. But this phone book can be messed with, can it? That sounds like a huge vulnerability.
You're right. DNS is absolutely critical, and yes, its vulnerabilities are serious. To clarify, it helps to understand three related concepts. Domain names, which are human-friendly, temporary names mapped to IP addresses, which are temporary logical addresses, and MAC addresses, which are considered permanent hardware physical addresses, though they can be spoofed.
Domain name, IP address, MAC address.
Got it. DNS uses a hierarchical naming scheme. It starts from top-level domains, TLDs, like .com or .org.
The ending part.
Right. Moving to registered domain names like google.com, and then subdomains or host names like www.google.com. Altogether, that forms a fully qualified domain name, FQDN.
FQDN, okay.
When a client wants to resolve an FQDN, it first checks its local cache. If it's not there, it queries a known DNS server. This process might involve several servers talking to each other. DNS operates over TCP for specific tasks like zone transfers, port 53, and mostly over UDP for standard queries, also port 53.
Port 53, good to remember. So
Oh.
how do we make this critical system more secure, given its importance and potential vulnerabilities?
The primary security improvement to the existing DNS infrastructure is DNS security extensions, DNSSEC.
DNSSEC.
Yes, DNSSEC provides authenticity and integrity for DNS data. It uses digital signatures to ensure that the DNS responses you get actually came from the authoritative server and haven't been tampered with. It prevents zone poisoning and cache poisoning.
So it signs the records.
Essentially, yes. More recently, DNS over HTTPS, DOH, and oblivious DOH, ODOH, have emerged. DOH encrypts DNS queries using HTTPS, hiding them from eavesdroppers on the network path.
Privacy for your lookups.
Exactly. ODOH goes a step further by adding a proxy between the client and the DNS resolver, separating the identity of the requesting client from the DNS resolver, thus providing anonymity and enhanced privacy for DNS queries.
Okay. DNSSEC, DOH, ODOH. Good improvements. But despite these, DNS is still susceptible to attacks. What exactly is DNS poisoning, and what are the ways attackers exploit it?
DNS poisoning is the general term for falsifying DNS information to redirect a client to a system the attacker controls, often a malicious website. It can happen in several ways.
Like sending someone to a fake bank website.
Precisely. One common method involves a rogue DNS server. An attacker might trick your computer into using their malicious DNS server, perhaps via DACP, and that server then provides false IP addresses for legitimate domains.
Okay.
Another is DNS cache poisoning, which targets the DNS servers themselves, not just the client. An attacker tries to inject incorrect DNS information into the cache of a recursive DNS server. If successful, anyone using that server gets the wrong address. This can propagate globally if intermediate caches pick it up.
That sounds widespread.
It can be.
Mm-hmm.
Closely related is DNS farming, which is malicious redirection, often achieved by modifying the local hosts file on a user's computer.
The hosts file.
Yeah, it's a local file that maps host names to IP addresses, checked before DNS. Or farming can happen via DNS spoofing. Finally, DNS query spoofing involves an attacker eavesdropping on a client's DNS query and raising to send a false reply with the correct query ID, QID, before the legitimate DNS server can respond. This often involves an adversary in the middle, AIATM position.
Wow, lots of ways to mess with the internet's phone book. So what are the best defenses against DNS poisoning?
Well, implementing DNSSEC is a major one, as it allows clients to validate the authenticity of responses.
Right, checking the signature.
Exactly. Organizations should also implement split DNS systems. This means using separate DNS servers for public queries, what the outside world sees, and internal queries for internal network resources. This prevents internal network details from being exposed publicly.
Keep internal stuff internal.
Yep. It's also crucial to strictly control DNS traffic at the firewall, block inbound and outbound UDP/TCP port 53 traffic, except for necessary communication with authorized upstream DNS servers or for zone transfers between your own servers.
Firewall rules are key.
Absolutely. Deploying network intrusion detection systems, NIDS, can help monitor for abnormal DNS traffic patterns indicative of poisoning attempts. Hardening DNS servers and client systems against general vulnerabilities is important too. And deploying DOH/ODOH on clients adds that layer of query privacy. Regular monitoring of DNS logs is vital for spotting suspicious activity.
And are there other DNS threats besides poisoning?
Yes. Domain hijacking, or domain theft, is where an attacker maliciously changes the registration details of a domain name, effectively stealing control of it from the legitimate owner. This might happen by compromising the owner's account at the domain registrar.
Ouch.
And homograph attacks leverage similarities in character sets. For example, using Cyrillic characters that look identical to Latin ones to register phony international domain names. Or IDAS. Someone might click a link thinking it's PayPal.com, but it's actually using a lookalike character, leading them to a phishing site.
Sneaky visual tricks. Okay, it's clear the basic IP communication isn't always secure. What are the key protocols that add crucial layers of protection to ensure our data isn't just delivered, but delivered securely?
Absolutely. We need specific protocols designed for security. One of the most important is Internet Protocol Security, IPsec.
IPsec.
Yes. IPsec is actually a suite of protocols that uses cryptography to provide confidentiality, encryption, integrity, anti-replay protection, access control, and message origin authentication. It's primarily used for virtual private networks, VPMS.
So VPNs heavily rely on IPsec.
Many do, yes. IPS can operate in transport mode, where it only encrypts or authenticates the payload of the IP packet, leaving the original header intact. Or it can operate in tunnel mode, where it encrypts or authenticates the entire original IP packet and then encapsulates it within a new IP packet. Tunnel mode is ideal for VPNs connecting entire networks.
Transport mode for end-to-end, tunnel mode for network-to-network.
Generally, yeah, that's a good way to think about it. Then we have Kerberos. Kerberos is a network authentication protocol designed to provide strong authentication for client-server applications using secret key cryptography. It's a cornerstone of Windows Active Directory authentication, for example, enabling single sign-on, SSO.
Kerberos for authentication.
Right. Another key one is Secure Shell, SSH. SSH provides end-to-end encryption for secure remote connectivity, replacing older insecure protocols like Telnet and WireLogin. It's also used for secure file transfer with SFTP.
SSH is essential for server admins.
Absolutely essential. The Signal protocol is another important one, though maybe less known in enterprise IT. It's a cryptographic protocol specifically designed for end-to-end encryption in voice calls, video conferencing, and instant messaging services. Apps like Signal and WhatsApp use it.
Ah, for messaging apps.
Yep. And finally, we have Transport Layer Security, TLS. TLS, and its predecessor, SSL, operates at OSI Layer 4, the transport layer. It's fundamental to encrypting the payload of TCP communications. This is what puts the S's in Hypertext Transfer Protocol secure, HTTPS.
So TLS secures web traffic?
Primarily, yes, but it can secure other TCP-based traffic too. TLS supports secure client-server communications, offering both one-way, server authenticates to client, and optionally two-way authentication, both authenticate to each other, using digital certificates.
Okay, IPsec, Kerberos, SSH, Signal, TLS, those are the big hitters for secure communication.
Definitely among the most important ones today.
When we layer protocols like HTTP, inside TCP, inside IP, inside Ethernet, it gets incredibly powerful and efficient. But you mentioned earlier, are there security downsides or implications of these multi-layer protocols?
There certainly can be, yes. While multi-layer protocols offer huge benefits, a wide range of options, encryption at various layers, flexibility, resilience, they also introduce specific drawbacks from a security perspective.
Like what?
Well, one significant concern is the potential for covert channels. These are hidden communication paths that can be used to exfiltrate data or control systems undetected, maybe by manipulating fields and protocol headers in unusual ways.
Hiding data in plain sight, sort of?
Exactly. Filters can also be bypassed. If an attacker encapsulates an unauthorized protocol inside an authorized one that the firewall allows, like tunneling FTP commands inside HTTP traffic, they might sneak past firewall rules designed to block FTP.
Tunneling to bypass rules.
Right. Finally, multi-layer protocols can sometimes allow logically imposed network segment boundaries to be overstepped. Depending on how things are configured, traffic might find unexpected paths between segments that were supposed to be isolated.
Interesting. So the layers can sometimes work against segmentation if you're not careful.
Potentially, yes. It requires careful design and configuration.
Networks are becoming more integrated with various services like voice, video, and storage, all running over a unified IP infrastructure. What does it mean when protocols converge?
Converged protocols refer exactly to that. The merging of specialty or proprietary protocols with standard ones, often utilizing the ubiquitous TCP IP suite. This allows for a more efficient and unified infrastructure, reducing the need for separate, dedicated networks for different services.
Consolidating onto IP.
Precisely. A prime example is Storage Area Network, SAN. Traditionally, SANs use dedicated protocols like fiber channel over separate cabling. But now, protocols allow SAN traffic to run over standard Ethernet and IP networks.
Like ISCSI.
Exactly. Internet Small Computer Systems Interface, ISCSI, is a perfect example. It's a networking storage standard that encapsulates SCSI commands. The language storage devices speak over IP at layer 5, the session layer, so your storage traffic travels over your regular network.
Makes sense.
Another massive example, probably the most common one you encounter, is Voice over Internet Protocol, VoIP.
VoIP phones everywhere.
Right. VoIP is essentially a tunneling mechanism that encapsulates voice and sometimes video data into IP packets, allowing phone calls and video calls to be made over the internet or private IP networks. It's largely replacing traditional public switch telephone network, PSTN, services.
But VoIP has its own security issues, doesn't it?
Oh, absolutely. While convenient, VoIP introduces several security considerations. Common attacks include caller ID falsification, often used in phishing, voice phishing, or spam, over internet telephony, SPIT.
Fake caller IDs trying to scam you.
Exactly. The call manager systems and the VoIP endpoints themselves are vulnerable to operating system and firmware attacks, just like any other computer. Adversary in the middle, AITM, attacks are a significant concern, allowing attackers to potentially intercept, listen to, or even manipulate calls.
Eavesdropping on phone calls.
Yes. And if the VoIP traffic isn't encrypted, it can be easily captured and decoded. To counter some of these threats, Secure Real-Time Transport Protocol, SRTP, is used. SRTP provides encryption, message authentication, and replay protection for the actual voice and video media streams in VoIP, often used alongside protocols like SIP for call setup.
SRTP for securing the actual voice data. Good to know. Okay, let's talk about a big shift in networking. Software-defined networking, SDN. This sounds quite different from traditional networking, where configuration is tied tightly to the physical hardware boxes. How does SDN work, and what are the benefits for management and security?
FDN is indeed a transformative approach. It fundamentally separates the network hardware's data plane from the control plane.
Data plane versus control plane.
Right. The data plane is the part of the network device, like a switch or router, that actually forwards the traffic based on instructions. The control plane is the brain that decides how the traffic should be forwarded, managing routing tables, access lists, etc.
Okay.
In traditional networking, both planes are tightly integrated within each physical device. SDN decouples them. The control plane logic is centralized in a software controller, which then programs the simpler data plane hardware devices.
So centralized brain controlling simple hardware.
Exactly. This allows for programmatic control over the entire network through software. The key benefits are dramatically simplified network management, increased flexibility. You can change network behavior by changing software, not rewiring or reconfiguring boxes individually, and the ability to adapt much more quickly to changing business needs. Application programming interfaces, APIs, are crucial here, allowing external software applications to interact with the SDN controller to automate network tasks.
That sounds powerful. Are there related concepts we should know?
Yes, SDN is often discussed alongside network functions virtualization, NFV. NFV involves virtualizing entire classes of network functions like firewalls, load balancers, routers, so they can run as software on standard hardware instead of requiring dedicated physical appliances.
Virtual firewalls, virtual routers.
Exactly. This further increases flexibility, scalability, and cost efficiency. We also have software-defined storage, FDS, which applies similar principles of abstraction and programmatic control to storage management. And an important evolution is software-defined wide area network, SDWAN.
SDWAN.
Yes, SDWAN uses SDN principles to manage wide area network links, often allowing organizations to intelligently route traffic over multiple connection types, like MPLS, broadband internet, LTE, based on application needs, performance, and cost, all managed centrally.
Okay, SDN, NFV, SDS, SDWAN, lots of software defining things.
It's definitely the trend towards more agile automated infrastructure.
Let's circle back to a core security principle, network segmentation. You described it earlier as dividing a large open office into smaller, secure departments. What are the different ways we achieve this segmentation?
Right. Network segmentation is about subdividing networks into smaller, more manageable units, subnets, segments, groups. The primary goals are improving performance by reducing broadcast traffic, simplifying management, and, most importantly from our perspective, providing security by isolating traffic and limiting the blast radius if one segment is compromised.
Containing the damage.
Exactly. We can achieve this through physical segmentation, where components or entire network segments are physically separated. No shared switches, no shared routers between them.
Physically separate wires and boxes.
Correct. The most stringent form of physical segmentation is air-gapped segmentation. This implies absolutely no direct physical or logical connection whatsoever between two systems and networks. They are completely isolated. Maybe data is transferred manually via USB drive if needed, with strict procedures.
The ultimate separation.
Yes. More commonly, though, we use logical segmentation, which uses switch-based techniques and software configuration to achieve isolation, even if devices share the same physical infrastructure.
Logical walls, not physical ones.
Good way to put it. Virtual Local Area Networks, VLANs, are a prime example. VLANs allow you to logically divide a single physical LAN switch into multiple separate broadcast domains. Devices within the same VLAN can communicate directly at Layer 2, but traffic between different VLANs must pass through a Layer 3 device, typically a router or a Layer 3 switch.
So the router enforces the rules between VLAN?
Precisely. Virtual private networks, VPNs, are another form of logical segmentation, creating secure, encrypted tunnels over potentially insecure networks like the Internet, effectively segmenting that remote user or site's traffic from the public network. And in cloud environments, a virtual private cloud, VPC, provides a logically isolated section of a public cloud, giving you control over your virtual network environment, including IP addressing subnets, routing tables, and network gateways, essentially segmenting your cloud resources.
VLANs, VPNs, VPCs, all ways to logically carve up the network.
Correct.
Now, microsegmentation takes this divide and conquer approach even further, right? Securing down to individual workloads or even applications. How does this work, and how does it relate to something like zero trust?
Microsegmentation is exactly that, taking segmentation to a much more granular level. Instead of just segmenting large network zones, like DMZ, internal database tier, microsegmentation aims to isolate individual workloads or applications from each other, even if they reside on the same network segment or even the same physical host.
Isolating individual servers or apps.
Yes, the goal is to drastically reduce the attack surface and prevent lateral movement. If one workload gets compromised, microsegmentation policies should prevent it from easily attacking its neighbors. This is often achieved using network overlays or encapsulation techniques, creating logical networks on top of the physical infrastructure, where security policies are enforced at the workload level.
Overlays, like VXLAN.
Virtual Extensible LAN, VXLAN, is a key enabling technology, yes. It's an encapsulation protocol that allows you to create a huge number of isolated Layer 2 segments, like VLANs, but far more scalable, that can span across physical network boundaries. Microsegmentation also heavily relies on distributed firewalls.
Distributed firewalls, not just at the perimeter.
Right. These are often software-based firewalls deployed directly on the hypervisor or even within the operating system of each workload. This includes internal segmentation firewalls, ISFWs, which are specifically designed to control traffic between internal segments or workloads, preventing that lateral spread of threats.
Firewalling between internal servers.
Exactly. And microsegmentation is a core tenet and enabler of a zero-trust architecture. Zero trust fundamentally assumes that no user, device, or application should be trusted by default, regardless of its location, inside or outside the traditional perimeter. Every connection attempt must be verified, authenticated, and authorized based on granular policies before access is granted. Microsegmentation provides the mechanism to enforce those granular policies at the workload level.
Never trust, always verify. Microsegmentation helps enforce that.
You got it.
Where do edge networks fit into all this? It sounds like the outer perimeter, or maybe where the action is closest to the user or device.
Edge networks are strategically designed architectures that push computing resources, processing power, data storage, applications closer to the physical edge of the network. This edge could be close to end users, IoT devices, remote offices, or anywhere data is generated or consumed.
Bringing the compute closer to the source user.
Exactly. The primary drivers are reducing latency and improving performance. By processing data closer to the source, you minimize the distance it has to travel back to a centralized data center or cloud, which is crucial for real-time applications like autonomous vehicles, industrial automation, or augmented reality.
Lower latency is key.
Definitely. Key concepts here include ingress points where data flows into the network edge and egress points where data flows out from the edge towards the core or other destinations. Managing security at these ingress-egress points is critical. Also, peering is important for edge networks.
Peering?
Peering is when different network operators, often at the edge, establish direct interconnections between their networks. This allows traffic to be exchanged directly between them, bypassing intermediary networks like the broader internet backbone. This improves performance, reduces latency, and can lower costs for traffic exchange between those peered networks.
Direct connections at the edge for speed. Okay, let's switch to something ubiquitous. Wireless networks. From home Wi-Fi to public hotspots, they're everywhere. What are the standards that govern them, and how do we even begin to set them up securely?
Wireless networking is indeed incredibly common due to its ease of deployment and relatively low cost.
Right.
But as you know, it's inherently more vulnerable than wired networks to things like eavesdropping, denial of service, DOS, attacks, and intrusions, simply because the signals travel through the air.
Anyone nearby could potentially listen in.
Potentially, yes. The core standard for wireless local area networking, what we commonly call Wi-Fi, is IEEE 802.11. Over the years, there have been numerous amendments like 802.1b, GN, AC, AX Wi-Fi 6, we have Wi-Fi 7, each offering better throughput using different frequency bands like 2.4 gigahertz, 5 gigahertz, and now 6 gigahertz with Wi-Fi 6E and 7, and introducing new features.
Wi-Fi standards keep evolving.
Constantly. Wireless networks can be configured in ad hoc mode, which is a direct peer-to-peer connection between devices without a central point, or more commonly in infrastructure mode, which uses a central wireless access point, WAP, that clients connect to.
The WAP is the central hub.
Right. Wireless networks are identified by an Extended Service Set Identifier, ESSID, or usually just Service Set Identifier, SSID. That's the network name you see when you scan for Wi-Fi.
The name you pick from the list.
Exactly. While some people think disabling the broadcast of the SSID, making the name hidden, enhances security, it's really not a true security measure. It's easily detected by network sniffers. It's security through obscurity, which is generally ineffective.
So hiding the name doesn't really help much.
Not against anyone slightly determined, no.
Wireless has definitely had a reputation for being insecure, especially thinking back to the early days, but security has evolved significantly, right? Can you walk us through that evolution of wireless security protocols? What's crucial to know today?
It has evolved massively, thankfully. The original security standard was Wired Equivalent Privacy, WEP.
WEP. I remember that being notoriously bad.
It was terrible. WEP used the Rivest Cipher 4 RC4 stream cipher, but its implementation had fatal flaws. It used static, shared keys, and the way it used the initialization vector, IV, was weak, making it incredibly easy to crack, often in minutes with readily available tools. If you see WEP anywhere today, it needs to be replaced immediately. Full stop.
Get rid of WEP. Got it.
As a temporary stopgap, Wi-Fi Protected Access, WPA, was developed. WPA introduced Temporal Key Integrity Protocol, TKIP, which was basically a wraparound RC4 designed to correct WEP's most glaring flaws. It offered improvements like per-packet key mixing, but TKIP itself was later found to have vulnerabilities, so WPA is also no longer considered secure.
WA was better, but still not good enough.
Correct. The real leap forward came with Wi-Fi Protected Access 2, WPA2. This is based on the robust IEEE 802.11i security standard. WPA2 mandates the use of Advanced Encryption Standard, AES, encryption, specifically implemented within counter mode with Cipher Block Chaining Message Authentication Code Protocol, CCMP.
WPA2 with AESCCMP. That sounds stronger.
Much, much stronger. AESCCMP provides strong confidentiality and integrity. WPA2 has been the standard for many years and is considered robust, although a significant vulnerability called Key Reinstallation Attack, KRACK, was discovered a few years ago, which could allow attackers under specific conditions to decrypt traffic. However, this is widely patched.
So keep WPA2 patched.
Definitely. The latest standard is Wi-Fi Protected Access 3, WPA3, finalized in 2018. WPA3 brings several improvements. It mandates even stronger 192-bit AECC LACMP encryption in its enterprise mode. Crucially, for personal networks, WPA3 Personal, it replaces the older pre-shared key PSK authentication method.
The single password everyone shares?
Right. It replaces that with simultaneous authentication of equals. SAE provides a much more secure initial key exchange using something called the Dragonfly Key Exchange, which is resistant to the offline dictionary attacks that plagued WPA2PSK. This makes guessing weak passwords much harder.
SAE and WPA3 sounds like a big improvement for home users.
It really is. In enterprise environments, both WPA2 and WPA3 often use IEEE 802.1x for authentication. 802.1x provides port-based network access control, ensuring clients are properly authenticated, often against a central server like Remote Authentication Dial-In User Service, RADIUS, before they're allowed onto the network. It's much more scalable and secure than shared passwords.
802.1x for enterprises. Okay. Beyond just Wi-Fi, what about other short-range wireless technologies like Bluetooth and NFC? Are they secure, and what are their specific threats we should be aware of?
Good question. These short-range technologies absolutely have their own vulnerabilities. Bluetooth, which is technically IEEE 802.15.1, is designed for personal area networks. PANs, connecting devices like headsets, keyboards, speakers over short distances. Bluetooth Low Energy, BLE, is a variant optimized for low power consumption, very common in IoT devices like fitness trackers.
Bluetooth is everywhere.
It is, but it's susceptible to various attacks. Blue sniffing involves passively capturing Bluetooth packets. Blue smacking is a type of denial of service attack. Bluejacking is sending unsolicited messages like contact cards to nearby Bluetooth devices. Blue snarfing is more serious. It's unauthorized access to information like contacts or calendars on a device via Bluetooth connection. And blue bugging is even worse, potentially giving an attacker remote control over certain phone functions.
Blue snarfing and blue bugging sound particularly nasty.
They are. Though modern devices have better protections, the key is usually keeping devices undiscoverable when not actively pairing and applying security updates.
Okay, what about RFID and NFC?
Radio frequency identification, RFID, is primarily a tracking technology using radio waves. You have passive tags powered by the reader's signal and active tags with their own power source. Used in inventory tracking, access cards, passports. Security concerns revolve around unauthorized reading, skimming of tags, and potential privacy implications.
Like someone reading your access card from a distance.
Potentially, yes, depending on the tag type and reader. Near-field communication, NFC, is a subset or standard related to RFID, designed for very close proximity communication, typically within 4 centimeters or about 1.5 inches. It's used heavily in contactless payment systems like tapping your phone or card, pairing devices quickly, and reading information tags.
Tap to Pay uses NFC.
Correct. Because the range is so short, eavesdropping is harder but not impossible. Attacks on NFC can include adversary in the middle during transactions, eavesdropping on the communication, data manipulation, and replay attacks, where captured communication is replayed later. The best practice for both RFID and NFC, especially on mobile devices, is generally to disable the feature when you're not actively using it to minimize the window of opportunity for attackers.
Turn off NFC when not needed. Good tip. We've touched on some specific attacks for different technologies, but let's maybe summarize the most common ways wireless networks, primarily Wi-Fi, are attacked more broadly.
Certainly. One very prevalent and dangerous attack is the deployment of rogue access points. These are unauthorized WAPs plugged into the corporate network, maybe by a careless employee or a malicious insider, or even placed nearby by an external attacker.
An unofficial WAP.
Right. They often bypass network security controls like firewalls or NAC, creating an unsecured backdoor. Attackers might also set them up to mimic legitimate SSIDs to lure unsuspecting clients into connecting to them.
Tricking users into connecting to the wrong network.
Exactly. A more sophisticated version of that is the evil twin attack. Here, the attacker sets up a fraudulent WAP that meticulously clones the identity of a legitimate one nearby same SID, maybe even same MAC address, through spoofing. They might then try to force legitimate users off the real WAP, perhaps using a de-authentication attack, encouraging them to reconnect to the stronger appearing evil twin.
Making their fake network look more attractive.
Precisely. Once a user connects to the evil twin, the attacker is in an adversary in the middle position, able to intercept, inspect, modify, or drop all the victim's traffic. They can steal credentials, inject malware, redirect users to phishing sites. It's very dangerous.
Evil twin sounds really bad.
It is. We also mentioned disassociation or de-authentication attacks. Attackers send spoofed management frames that tell clients to disconnect from the legitimate WAP. This can be used simply as a denial of service, kicking users off the network, or as a setup step for an evil twin attack, as we just discussed, or to capture the handshake when the user reconnects, which can be used in attempts to crack the Wi-Fi password.
Forcing a disconnect.
Oh. Jamming is another DOS technique where an attacker floods the wireless frequencies with noise or interfering signals, effectively preventing legitimate communication. Finally, a replay attack involves capturing legitimate wireless communications, maybe an authentication handshake, and then retransmitting or replaying it later to try and gain unauthorized access or impersonate a legitimate user.
Rogue APS, evil twins, death attacks, jamming, replay. Lots to watch out for in the wireless world.
Definitely keeps wireless security professionals busy.
Moving beyond our local networks, how does our data travel across the globe? Thinking about technologies like satellites or the cellular networks our phones use, what are the key considerations and potential security issues there?
Good question. The global infrastructure is fascinating. Satellite communications play a huge role, especially for remote areas, maritime, aviation, and broadcast. Satellites operate in different orbits, low Earth orbit, LEO, medium Earth orbit, MEO, and geostationary orbit, GEO.
LEO, MEO, GEO. What's the difference?
It's about altitude. LEO satellites, like those used by SpaceX's Starlink, are closer to Earth, maybe a few hundred to 2,000 kilometers up. This means lower latency, less signal delay, but they move fast relative to the ground, so you need a large constellation of them for continuous coverage. MEO is in between. GEO satellites are much higher, about 36,000 kilometers, and orbit at the same speed the Earth rotates, so they appear stationary in the sky. This is great for broadcasting to fixed locations, but the distance means higher latency.
Higher orbit, higher latency.
Generally, yes. Security considerations for satellite communication include the potential for signal interception if the links aren't properly encrypted, jamming of signals, and securing the ground stations that control them.
Okay. And cellular networks.
Cellular mobile networks are, of course, vital. We've seen a dramatic evolution from 2G, basic digital voice and text, through 3G, mobile internet, 4G LTE, faster mobile broadband, and now to 5G.
5G is the big buzzword now.
It is. 5G offers significant advancements. It uses high-frequency bands for much greater bandwidth, promises much lower latency, critical for real-time applications, and is designed to support a massive number of connected devices, enabling the Internet of Things, IoT, on a grand scale.
So faster speeds, lower delay, more devices.
That's the promise. However, cellular networks also have security concerns. While communications between your phone and the tower are generally encrypted, especially in 4G, 5G, the strength and implementation can vary. There have been vulnerabilities discovered in the underlying protocols over the years. Wireless sniffing, capturing cellular signals is possible, although decryption is difficult without keys. A more significant concern is the potential for adversary-in-the-middle attacks using fake cell towers, sometimes called IMS eye catchers or stingrays.
Fake cell towers.
Yes. These devices can trick phones into connecting to them instead of the legitimate network. Depending on the device's sophistication, they might be able to intercept calls, texts, data traffic, track device locations, or even push malware. Law enforcement uses them, but criminals can build them too. Securing the core network infrastructure itself is also a major ongoing effort for carriers.
Fake towers sound scary. Okay, let's shift back towards content. Ever wonder how, say, Netflix videos or popular websites load so fast, even if their main servers are geographically far away? Content distribution networks, CDNs, play a big role there, right? What are they and how do they impact data flow?
Absolutely. CDNs are essential for the performance of the modern internet. A content distribution network, or CDN, is a geographically distributed network of proxy servers and their data centers. Their goal is to provide high availability and performance by distributing the service spatially relative to end users.
Bringing the content closer to the user.
Exactly. Instead of every user in, say, Europe pulling a video file or website image from a single server in California, the CDN caches copies of that content on servers located much closer to the European users, maybe in Frankfurt or London. When a user requests the content, they are directed to the nearest CDN edge server holding a copy.
So less distance means faster loading.
Precisely. It reduces latency, reduces bandwidth consumption on the origin server, improves loading times, and can even help absorb traffic spikes and mitigate some types of DOS attacks by distributing the load. Major companies like Akamai, Cloudflare, Amazon CloudFront operate massive CDNs.
Okay, CDNs are all about distributed performance.
And availability, yes.
Now, let's talk about secure network segments within an organization again. It's like having different security zones. What are the common ones we create, like intranets, extranets, and the famous DMZ?
Right. Defining specific network segments based on trust levels and purpose is fundamental to network security design. The two most basic are intranets and extranets.
Intranet versus extranet.
An intranet is a private internal network designed for exclusive use by an organization's internal employees. It hosts internal resources, company information, internal applications, etc. It's generally considered a trusted zone, although zero-trust principles challenge that assumption. An extranet, on the other hand, is a controlled extension of an intranet. It allows authorized external users like business partners, suppliers, or key customers to access specific internal services or data in a secure and controlled manner without giving them full access to the entire intranet.
Controlled access for outsiders.
Exactly. Then we have the crucial screen subnet, more commonly known as a demilitarized zone, or DMZ.
The DMZ sounds military.
The name evokes that image of a buffer zone, and that's exactly what it is. A DMZ is a special-purpose network segment, logically located between the untrusted internet and the trusted internal network. It's designed to host public-facing servers and services that need to be accessible from the internet, like the company website, email servers, MTAS, external DNS servers.
Servers that need to face the public internet.
Right. The idea is that these servers are inherently more exposed to attack.
Yeah.
By placing them in the DMZ, you isolate them. A common DMZ architecture uses two firewalls, an external firewall between the internet and the DMZ, and an internal firewall between the DMZ and the trusted internal network.
2 layers of firewall.
Yes. This creates that buffer. If a server in the DMZ gets compromised, the attacker still has to get through the second internal firewall to reach the sensitive internal network. The rules on the internal firewall are typically much stricter.
Protecting the crown jewels inside.
Precisely. We also sometimes talk about traffic directionality. North-south traffic refers to traffic flowing in and out of the data center or network. For example, user accessing a web server from the internet. East-west traffic refers to traffic flowing laterally between servers or segments within the data center or internal network. Securing east-west traffic has become increasingly important with micro-segmentation and preventing lateral movement.
North-south is perimeter traffic, east-west is internal traffic. Got it. It's not just the software and protocols, the physical hardware that makes up our networks. The routers, switches, firewalls themselves needs to be secure and reliable too. What are the key aspects of secure hardware operation?
That's a critical point often overlooked. The secure and reliable operation of the hardware itself is paramount for overall network availability and resilience. One of the most basic but vital aspects is ensuring redundant power.
Redundant power supply.
Yes. Critical network devices should ideally have dual power supplies connected to different power circuits. Additionally, they should be protected by an uninterruptible power supply, UPS, to handle short outages and brownouts, and surge protectors to guard against voltage spikes. This is fundamental for high availability.
Keeping the lights on, literally.
Exactly. Beyond power, proper hardware management involves having personnel with specialized training to configure and maintain the devices securely. It also means having solid vendor support contracts in place.
Support contracts.
Absolutely. For critical infrastructure, you need timely hardware replacement if something fails, access to software updates and security patches, and expert support from the vendor when complex issues arise. Understanding warranty limitations is also important. In essence, strong support contracts, warranties, and competent personnel are just as vital as the hardware specs themselves for ensuring secure and continuous operation. You don't want your core router failing with no quick replacement or support available.
Good point. The operational side is key. Okay, let's quickly review some of the core pieces of network equipment we find in secure networks, maybe moving up the OSI layers again, focusing on their role and security relevance.
All right, good idea. Starting at layer 1, the physical layer, we have basic signal-level devices. Repeaters regenerate a signal to extend its range. Hubs are simple multi-port repeaters. They take a signal coming in one port and broadcast it out all other ports. They operate in a single collision domain, meaning if two devices transmit at once, the signals collide and data is corrupted. Hubs are largely obsolete now due to inefficiency and security issues. Easy eavesdropping. Hubs are dumb, basically.
Pretty much, yeah. Moving up to layer 2, the data link layer, we have bridges. Bridges connect two network segments and make forwarding decisions based on MAC addresses learned on each segment. They were an improvement over hubs because they segmented collision domains. Switches are essentially multi-port bridges, much more advanced.
Switches are smarter.
Definitely. Switches learn which MAC address live off which port and forward frames only to the necessary destination port rather than broadcasting like a hub. This creates separate collision domains per port, drastically improving performance and security, makes eavesdropping much harder. Most modern switches support things like VLANs for logical segmentation. Some switches also have layer 3 capabilities, layer 3 switches or multi-layer switches, meaning they can perform routing functions, often used for routing between VLANs within a LAN.
Okay, switches are central to modern LANs. Absolutely. Then there's multi-protocol label switching, MPLS. This is more of a WAN or service provider technology, operating somewhere between layer 2 and layer 3. MPLS speeds up traffic forwarding by adding short labels to packets at the edge of the MPLS network. Routers inside the MPLS cloud make forwarding decisions based on these simple labels instead of doing complex IP lookups, resulting in faster, more predictable performance.
MPLS uses labels for speed.
Correct. Routers, as we discussed, operate primarily at layer 3, the network layer. Their main job is controlling traffic flow between different networks or subnets based on logical IP addressing, using routing tables to determine the best path. They're fundamental for connecting different network segments and connecting to the internet.
Routers connect networks.
Yes. A jump box, or jump server, is a specialized hardened system used to manage devices in a separate security zone. You connect securely to the jump box first, and then from there you connect to the target systems, like servers in a DMZ or a secure internal segment. It acts as a controlled, audited gateway for administrative access.
A secure stepping stone for admins.
Exactly. For security monitoring, you have sensors. These are devices or software agents that collect information, like network traffic logs, system events, and transmit it for storage and analysis, often feeding into a security information and event management (SIEM) system or a security orchestration, automation, and response (SOAR) platform.
Sensors feed the SIEM.
All right. And finally, a quick mention of system on a chip, SoC. This isn't a network device per se, but many network devices, like routers, firewalls, IoT devices, are built using SoCs. An SoC integrates most or all components of a computer or electronic system onto a single chip. While efficient, their security relies heavily on the security of the integrated firmware and operating system, making patching and vulnerability management critical for devices using them.
SoCs are integrated chips inside many devices.
Yeah, very common now.
How do we control who and what gets onto our network in the first place? Access control seems critical. Network access control, NAC, sounds like the key technology here.
Network access control, NAC, is indeed crucial for enforcing policy at the point of network entry. It's a combination of concepts and technologies designed to enforce strict security policy adherence before and possibly during network access.
Controlling access from the start.
Exactly. The primary goals of NAC are to prevent unauthorized or non-compliant devices from accessing network resources, enforce security policies, like requiring up-to-date antivirus or patches, and potentially use user or device identity to grant differentiated levels of access.
So checking device health before letting it in.
That's a major part of it. NAC often operates based on one of two main philosophies: pre-admission or post-admission. Pre-admission means a system must meet all security requirements before it's granted any significant network access. It might be quarantined first if it fails checks. Post-admission grants some initial, possibly limited access, and then monitors the device's activities and compliance, potentially revoking or changing access levels based on behavior or policy violations.
Check first or let in and monitor.
Right. NAC solutions can be implemented using host system agent software installed on the client devices that reports health status back to the NAC server, or using agentless techniques which try to assess the device's posture remotely, using network scanning and other methods. Agent-based is generally more thorough, but requires managing the agent software.
Agent versus agentless, trade-offs there.
Definitely. NAC is a powerful tool for reducing risk from compromised or unauthorized endpoints connecting to the network.
Okay, let's talk firewalls. They're probably the most recognized network security device, like the digital bouncers or gatekeepers for our networks. What are the different types, and how do they work to protect us?
Firewalls are absolutely fundamental. They are tools, hardware appliances, software, or cloud services designed for managing, controlling, and filtering network traffic between different network segments, typically between a trusted internal network and an untrusted external one, like the internet, or between different internal segments like the DMZ and the internal LAN.
The network gatekeepers.
Exactly. A core operational concept for most firewalls is deny by default, also known as implicit deny. This means that unless traffic is explicitly permitted by a specific rule, it is denied. This is a much safer posture than allowing everything except what's explicitly denied.
Deny unless specifically allowed. Safer.
Much safer. Firewall rules define what traffic is allowed, often based on source of destination IP addresses, port numbers, protocols, and sometimes application or user identity. Firewalls can take several actions on traffic that matches a rule or the default deny. They can deny or reject it, blocking it and often sending an error back, drop it, silently discarding it without notification, which is often preferred as it doesn't give attackers information, or simply alert on it while allowing it. The order of rules is critical, as firewalls typically apply a first-match rule logic. The first rule that matches the traffic determines its fate.
Rule order matters.
Hugely. A related concept is the bastion host. This is a system, often a firewall appliance itself, or maybe a jump server, that is specifically hardened and designed to withstand attacks because it sits exposed, like a fortified guardhouse or bastion in a medieval castle wall.
Hardened because it's exposed.
Precisely. Firewalls also perform ingress filtering, checking incoming traffic, e.g. blocking packets with internal source IPs coming from the internet, which indicates spoofing, and egress filtering, checking outgoing traffic, e.g. preventing internal systems from initiating connections to known malicious sites or sending out sensitive data. Egress filtering is often overlooked, but very important.
Checking traffic both ways. Good. Now, what about the different types of firewalls?
Right, firewalls have evolved significantly. The earliest were static packet filtering firewalls, often implemented on routers, screening routers. They operate at layer 3 network and layer 4 transport, making decisions based purely on the header information in each packet. Source to destination IP, source to destination port. Protocol type. They are stateless, meaning they evaluate each packet individually without any memory of previous packets in the same conversation. Simple, fast, but limited.
Stateless, just looking at headers.
Yes. Then came application-level firewalls, ALSS, sometimes called proxy firewalls. These operate up at layer 7 application. They understand specific application protocols like HTTP, FTP, SMTP, and can make much more granular decisions based on the application commands or content, not just addresses and ports. A common example today is a web application firewall, WAF.
WAFs protect web apps specifically.
Exactly. WFs are specialized ALFS, designed to protect web applications from attacks like SQL injection, cross-site scripting, XSS, and others by inspecting HTTP, HTTPS traffic. They can be physical appliances, server add-ons, plugins, or cloud-based services. Advanced WAFs are often part of Secure Web Gateway, SWG, or Next Generation Secure Web Gateway, NGSWG, solutions, which bundle WAF capabilities with other security features like TLS decryption, Cloud Access Security Broker, CISSP functions, Advanced Threat Protection, ATP, sandboxing, machine learning-based threat detection, and data loss prevention, DLP.
Lots of features in modern web gateways.
Indeed. Another type is the circuit-level firewall or circuit proxy. These operate at layer 5 session. They don't inspect application content, but instead validate the TCP handshake and session establishment between trusted partners. Once the session is approved, they allow traffic to flow relatively unimpeded. The SOCKS protocol is often associated with circuit-level proxies.
Validating the connection itself.
Right. A major advancement was the Stateful Inspection Firewall, SIF, also known as Dynamic Packet Filtering Firewalls. These are much more intelligent than static filters. They operate primarily at layers 3 and 4, but maintain a state table that tracks active connections. They understand the context of traffic. Is this packet part of an already established session? Is it a valid response to an outgoing request? This allows them to dynamically create temporary rules to permit return traffic for legitimate connections initiated from inside while still blocking unsolicited incoming traffic. Most firewalls today are stateful.
Stateful remembers the conversation. Much smarter.
Much smarter, yes. Many stateful firewalls also incorporate deep packet inspection, DPI. This goes beyond just looking at headers. DPI examines the actual payload or content of the packets. This allows the firewall to identify specific applications regardless of the port they use, detect malware signatures, block certain types of content, or enforce application-specific policies.
DPI looks inside the packets.
Correct. This leads us to next-generation firewalls, NGFWs. These are essentially multifunctional devices, MFDs, sometimes called Unified Threat Management, UTM systems. NGFWs combine traditional stateful inspection with many other security features integrated into a single platform, such as application awareness and control using DPI, integrated intrusion prevention systems, IPS, web content filtering, VPN anchoring, and often anti-malware inspection.
NGFW bundles multiple security tools.
Exactly. We should also mention host-based firewalls. These are software firewalls running directly on individual computers, endpoints, like the Windows firewall or IPTables on Linux. They provide protection at the endpoint itself, controlling traffic entering and leaving that specific machine. And finally, internal segmentation firewalls, ISFWs. As the name implies, these are deployed within the internal network, specifically to control traffic flow between different internal segments or VLANs, helping to prevent the lateral spread of threats if one part of the internal network is compromised.
Firewalls inside the network too, not just at the edge.
Increasingly important, yes. Oh, and related to application and circuit firewalls are proxy servers. Proxies act as intermediaries. A forward proxy sits in front of internal clients and makes requests to external servers on their behalf, often used for content filtering, caching, and hiding internal client IPs. A reverse proxy sits in front of internal servers, like web servers, and accepts requests from external clients on behalf of the servers, often used for load balancing, SLTLS, encryption, decryption, and protecting the backend servers.
Forward proxy for clients, reverse proxy for servers. Got it.
And proxies can be transparent. Clients don't need special configuration, or non-transparent. Clients need to be configured to use the proxy.
Okay, that covers a lot of firewall ground. Beyond the network perimeter and the firewalls guarding it, how do we secure the actual devices users work on, the endpoints? Desktops, laptops, mobile phones. They're everywhere, often outside the corporate network, and seem like prime targets.
This is where endpoint security comes in, and you're absolutely right, it's critical. While network security devices like firewalls and proxies manage traffic flow between systems, endpoint security focuses on protecting the individual host or client device itself.
Securing the actual computer or phone.
Yes. The challenge, as you noted, is that these environments are highly distributed. Users have varying levels of technical expertise, devices might connect from untrusted networks, and endpoints are constantly targeted by malware, phishing, and other threats. They are often the initial point of compromise and breaches.
So what are the key safeguards for endpoints?
It's a multi-layered approach. Robust email screening to filter out malicious attachments and links is crucial. Strict policies on downloading and uploading files, especially from the internet, are needed. Strong access controls on the endpoint itself requiring strong passwords or multi-factor authentication, limiting user privileges, least privilege principle, are fundamental. Using restricted user interface mechanisms where appropriate can limit what users can accidentally do.
Limiting user actions.
Right. File encryption, especially full disk encryption, is crucial for protecting data at rest on laptops or mobile devices if they are lost or stolen. Using screensavers with password protection is a simple but effective physical security measure. Data classification helps identify sensitive data that needs stronger protection. Regular backups are essential for recovery from ransomware or hardware failure. And critically, continuous security awareness training for users is perhaps one of the most effective defenses against things like phishing.
Training users is key.
Absolutely. In terms of more advanced technical solutions, we have endpoint detection and response, EDR.
EDR?
Yes. EDR solutions go beyond traditional antivirus. They continuously monitor endpoint activities, process execution, file changes, network connections, registry modifications, looking for suspicious behavior patterns or indicators of compromise that might signal an advanced threat. They record this activity, allowing security teams to investigate incidents, understand how a compromise happened, the attack chain, and respond by isolating the endpoint, terminating malicious processes, or removing malware.
So EDR is like a security camera and response team for the endpoint.
That's a great analogy. It provides deep visibility and response capabilities. You'll also hear related terms like managed detection and response, MDR, where a third-party provider manages the EDR tool and provides the security monitoring and response service. Endpoint Protection Platform, EPP, often refers to a suite that combines traditional antivirus with other protection capabilities like host firewall, device control, and sometimes basic EDR features. And Extended Detection and Response, XDR, aims to break down security silos by integrating telemetry and response actions across multiple security layers. Endpoint, EDR, network, email, cloud, providing a more unified view of threats across the entire environment.
EDR, MDR, EPP, XDR, the endpoint security space is evolving fast.
It really is, reflecting the importance of securing those endpoints.
Now let's get down to the very physical connections again, the cables, the airwaves, the fundamental infrastructure that carries all this data. What about cabling types, network topology, and the technologies of the transmission media themselves?
All right, this takes us back to the foundations, often at layer 1. First, it's useful to differentiate between local area networks, LAANs, which typically cover a limited geographical area like a single building or campus, and wide area networks, WANs, which span larger distances, connecting geographically dispersed LANs or remote users, often using leased lines or public networks like the internet.
LAN is local, WAN is wide.
Exactly. The transmission media refers to the actual physical pathways that data signals travel through. Key factors when choosing media include signal propagation quality, physical security, is it easy to tap, and whether encryption is needed over that medium.
What affects signal quality?
Several factors impact how well a signal travels. Attenuation. This is a natural loss of signal strength as it travels over distance. All media have attenuation. Repeaters are used to boost the signal. Interference. External signals can interfere with the data signal. Common types are electromagnetic interference, EMI, from motors or power lines, and radio frequency interference, RFI, from radio transmitters or other wireless devices. Shielding can help mitigate this. Noise. Random fluctuations or disturbances that can corrupt the signal. Jitter. This is the variation in the delay, latency of received packets. High jitters can be problematic for real-time applications like voice or video. Bandwidth. The data carrying capacity of the medium, usually measured in bits per second. Propagation delay latency, the time it takes for a signal to travel from sender to receiver.
Attenuation, interference, noise, jitter, bandwidth, latency, all impact performance.
Okay, what about the actual cabling types? Historically, coaxial cable, or coax, was popular, especially for early Ethernet, like 10 base 2 and 10 base 5 in cable TV.
Yeah.
It has a central copper conductor, insulation, a braided metal shield, and an outer jacket. It offered good bandwidth and shielding for its time, but can be bulky and susceptible to issues if bent too sharply.
The old thick Ethernet cables.
Right. Much more common today for LANs is twisted pair cabling. This comes in two main varieties: shielded twisted pair, STP, which has a metallic foil shield around the pairs to reduce interference, and unshielded twisted pair, UTP, which relies solely on the twisting of the wire pairs to cancel out interference and crosstalk. UTP is more common and less expensive.
Why twisted?
The twisting causes interference picked up by one wire in the pair to be largely canceled out by the interference picked up by the other wire, significantly reducing noise. UTP cables are categorized by performance: Cat1, old fun wire; Cat3, 10 MEP, Cat55E, 100 MEP, Cat66A, 1 Gbps, 10 Gbps, Cat7, Cat8, even higher speeds. Higher categories support higher bandwidth over specific distances.
Cat5e and Cat6 are pretty standard now.
Yes, for gigabit Ethernet. The other major player, especially for backbones and longer distances, is fiber optic cable. Instead of electrical signals, fiber transmits pulses of light down thin strands of glass or plastic.
Light instead of electricity.
Correct. This gives fiber huge advantages: extremely high bandwidth potential, very low attenuation, signals travel much farther, immunity to electromagnetic interference since it uses light, and excellent security. It's very difficult to tap a fiber cable without disrupting the signal and being detected.
Fiber sounds superior in many ways.
It is, but it's generally more expensive to install and requires specialized equipment. Fiber comes in two main types: single-mode fiber, SMF, which has a very thin core and uses lasers, allowing signals to travel many kilometers, used for WANs and long backbones; and multi-mode fiber, MMF, which has a larger core, uses cheaper LEDs, and is suitable for shorter distances within buildings or campuses, up to a few hundred meters typically.
Single mode for long haul, multi-mode for shorter runs.
Generally, yes. And the technology used with fiber is dense wavelength division multiplexing, DWDM. This allows multiple data streams to be transmitted simultaneously over a single fiber strand by using different wavelengths, colors of light for each stream, dramatically increasing the capacity of existing fiber infrastructure.
Multiple colors of light on one fiber. Cool. Networks aren't just random cables strung together. They have specific physical or logical layouts or topologies. How do these different designs impact network performance and security?
Right. The transport architecture, or network topology, refers to how network devices are physically or logically interconnected. Understanding topology is key to predicting performance, identifying potential bottlenecks or single points of failure, and planning for redundancy. We also sometimes talk about different planes of operation within network devices.
Planes, like data plane, control plane.
Exactly. The data plane, or forwarding plane, is responsible for the actual high-speed forwarding of user data packets based on decisions made by the control plane. The control plane is the brain that runs routing protocols, builds forwarding tables, manages sessions, etc. The management plane is used for configuring, monitoring, and managing the device itself, example via SSH or SNMP. Separating these planes, as SDN does conceptually, is important for scalability and security.
Okay. Now for the common network topologies.
Let's run through the classics. A ring topology connects devices in a physical or logical circle. Data typically circulates in one direction, often using a token passing mechanism like token ring to control who can transmit. A single break in the ring can break down the entire network unless fault tolerance mechanisms like dual counter-rotating rings in FDDI are used. Security-wise, every node sees the traffic. A bus topology connects all systems to a single shared backbone cable, the bus. Data sent by one device is broadcast along the entire bus, and only the intended recipient accepts it. Requires terminators at each end. Simple and cheap initially, but the shared bus is a single point of failure. Performance degrades under heavy load due to collisions, if using older protocols like early Ethernet, and eavesdropping is easy. A star topology is probably the most common LAN topology today. All devices connect directly to a central device, typically a switch, historically a hub. It's easy to install and manage. A break in one cable only affects that one device. However, the central device is a single point of failure. If the switch dies, that segment goes down. A mesh topology interconnects devices with multiple paths. In a full mesh topology, every device is connected directly to every other device. This offers extremely high redundancy and resilience. Multiple paths exist if one link fails. However, it's very expensive and complex due to the sheer number of connections required, especially in large networks. A partial mesh connects some devices with multiple links, providing redundancy where it's most critical, offering a balance between cost and resilience. The Internet itself is a complex mesh. Ethernet, while technically a set of standards, i.e. E802.3, often implies a logical bus, or more commonly with switches, a physical star topology. It originally used shared media leading to collision domains, but modern switched Ethernet with full duplex communication largely eliminates collisions on point-to-point links between a device and a switch port.
Ring, bus, star, mesh. Different layouts with different trade-offs in cost, performance, and reliability.
Exactly. The choice depends on the specific requirements.
Finally, let's quickly touch on some very fundamental communication concepts that underpin everything we've discussed: analog versus digital, synchronous versus asynchronous, and casting methods.
Absolutely, these are core ideas. First, analog and digital communications. Analog signals are continuous and vary smoothly over time, representing information through changes in wave characteristics like amplitude or frequency, think old broadcast radio or vinyl records. Digital signals are discrete, representing information using distinct on-off pulses or voltage levels, typically corresponding to binary ones and zeros. Digital communication is generally more reliable, less susceptible to noise, easier to encrypt, and the basis for all modern computing and networking.
Digital is bits, analog is waves.
Good summary. Next, synchronous and asynchronous communications. This relates to timing. Synchronous communications require the sender and receiver to share a common clock signal or timing mechanism. Data is transmitted in continuous blocks or frames, synchronized by the clock. This allows for very high data rates because there's less overhead, but requires precise timing. Asynchronous communications, on the other hand, do not use a shared clock for continuous synchronization. Data is typically sent character by character, or byte by byte, with each character framed by start and stop bits to tell the receiver when it begins and ends. Simpler to implement for intermittent traffic, but has more overhead and lower maximum speeds. Think of a standard serial port, RS-232, that's often asynchronous.
Synchronous needs a clock. Asynchronous uses start-stop bits.
Right. And finally, casting technologies. This refers to how data is addressed to one or more recipients. Broadcast. Data is sent from one source to all possible recipients within a specific network segment or broadcast domain, is LAARP request, DHCP discovery. Multicast. Data is sent from one source to multiple specific recipients who have explicitly joined a multicast group, e.g. streaming video to subscribers, some routing protocol updates. More efficient than sending multiple unicast streams. Unicast. Data is sent from one source to a single specific recipient, e.g. browsing a website, sending an email. This is the most common form of communication. Anycast. Data is sent from a sender to the nearest node among a group of potential receivers that all share the same anycast address. This is often used for things like distributing DNS services or CDN content. Your request goes to the geographically closest server. Geocast. A less common type where data is sent to all devices located within a specific geographic region.
Broadcast, all. Multicast, some. Unicast, one. Anycast, nearest. Geocast, area. Got the distinctions.
Excellent. Understanding those fundamentals really helps make sense of the higher-level protocols and architectures. Well, what a journey we've had through CISSP Chapter 11. Secure Network Architecture and Components. We've really covered a lot of ground. We started with the foundational concepts, the OSI and TCP, PIP models. The key takeaway there, I think, is that these models aren't just academic exercises. They're our roadmap. They help us understand how data travels, how it gets encapsulated and de-encapsulated, and crucially, they show us where to implement security controls and where vulnerabilities might exist at each stage of communication.
We really did. And from there, we dove into the intricacies of IP addressing IPv4, the transition to IPv6, CIDR, and the absolutely vital role of DNS, the Internet's phone book, along with its surprising vulnerabilities like poisoning and spoofing. It was fascinating to see how fundamental protocols like ARP, despite their simplicity, can be exploited for things like man-in-the-middle attacks, highlighting that need for vigilance even at those lower layers.
Absolutely. Then we moved into the essential security strategies of network segmentation. We talked about physical separation like air gaps, but more commonly logical segmentation using VLANs, and we touched on how micro-segmentation takes that even further, isolating individual workloads, which is so key for zero trust, and preventing lateral movement if or perhaps when a breach occurs. Understanding how these divisions protect assets is just fundamental to containing damage.
And we didn't stop there. We explored the unique challenges and the constantly evolving security landscape of wireless networks. We traced the history from the, frankly, disastrous WEP up to the much more robust WPA3 with SAE. And we looked beyond Wi-Fi at Bluetooth and NFC, recognizing they have their own attack vectors like blue snarfing or NFC replay. It's a clear reminder that security is a continuous arms race, especially in the wireless realm.
So true. We also broadened our view to the underlying infrastructure, global communication via satellites and cellular networks, the performance magic of content delivery networks, CDNS. And we drilled down into the vital network equipment that forms the backbone, the routers making path decisions, the switches connecting devices efficiently, and of course the many types of firewalls standing guard stateful, next-gen, WAFs, internal segmentation firewalls. It's also a stark reminder, as we discussed, that physical security, redundant power, even support contracts for this hardware, they all play a role in the overall digital defense posture.
Exactly. We wrapped up with how network access control, NAC, systems act as the gatekeepers, checking credentials and device health before granting network access, and the paramount importance of endpoint security, protecting those laptops, desktops, and mobile devices where users actually work and data resides. This shift towards solutions like EDR and XBR really underscores that the perimeter isn't enough anymore. Every single device is a potential entry point that needs protection and monitoring.
Understanding all these layers, components, protocols, and design principles isn't just academic knowledge for an exam. It's absolutely essential for anyone involved in building, managing, or defending resilient, secure systems in today's incredibly interconnected world. It's really about recognizing that every connection you make, every piece of data you send or receive, traverses this complex architecture, an architecture designed to keep it safe, or, if misconfigured or outdated, potentially leave it vulnerable.
That's a great way to put it. So, maybe a final thought for you, the listener. Think about the next time you connect to a public Wi-Fi network, or maybe even just send an email. What layers of security or perhaps potential vulnerabilities are at play behind the scenes that maybe you never even considered before this deep dive? Hopefully, you now feel much more informed and empowered to understand the hidden world of secure network architecture. Until next time, keep listening, keep learning.